The number of confirmed existing exoplanets is something that changes almost daily. Currently, there are 861 confirmed exoplanets, about 25 of which many scientists agree upon labeling as potential habitable exoplanets, and about 8 that several scientists have given the title of habitable planet candidates. Such habitable exoplanet candidates are Gliese 581g, Kepler 22b, and Kepler 47c, just to name a few. The closest of these potentially habitable exoplanets lie at around 20 light-years from Earth, but some, such as Kepler 47c, are close to 5,000 light-years away. In order to be considered potentially habitable, these exoplanets must be similar to the only known place that harvests life thus far, Earth. In other words, these exoplanets must have suitable gravity, atmosphere, and resources to promote life. Therefore, the size of the planet and distance from its host star is crucial for the planet's habitability. Whether or not life on these planets exists remains unknown for now, but with so many exoplanets being discovered so often, scientists will surely soon know the truth behind these Earth-like exoplanets and the possibility of life among them.
In the search for exoplanets, it remains a difficulty for the world scientists to find them due to many challenging reasons. One being that planets don't produce much light on their own. Another is that they're very far from Earth, which makes it hard for us to detect them. And they are also lost in the light of nearby stars. One method that we have of finding exoplanets is the radial velocity method, which measures slight changes in a star's velocity as the star and the planet move about their common center of mass. Astronomers can tell from the light waves whether the movement is away or towards, with the blue shift being towards and away as a red shift. This is the same as a sound from a car horn on Earth. The larger the planet and the closer it is to the host sun, the faster the star moves about the center of mass, causing a larger color shift in the spectrum of starlight. This is why it's easier to find Jupiter-class planets with this method, which is a difficulty when we're looking for Earth-like exoplanets. Another method that we have is measurement of the effect on the sun producing back and forth motion that can be detected by an observer positioned several light years away. Instruments precisely measure the position of stars as compared to other stars around them, and are thus able to detect any movements in the star's position due to the wobbling caused by an orbiting exoplanet. The transit method deals with if a planet passes directly between a star and an observer's line of sight, it blocks out a tiny portion of the star's light, thus reducing its apparent brightness. Sensitive instruments can detect this periodic dip in brightness, and from this the astronomers can find the orbit and the size of the planetary companion. Earth-like planets would make a small dip, which is why they're harder to find, but this method will find. Direct imaging is another method which takes actual pictures of exoplanets. This is extremely difficult because of how bright stars are near them, but there have been several breakthroughs with it, and a handful of exoplanet images have been made possible. Gravitational microlensing is another method in which a planet happens to pass in front of a star along our line of sight. The planet's gravity will behave like a lens. This focuses the light rays and causes a temporary sharp increase in brightness and changes the apparent position of the star. Astronomers can use the gravitational microlensing effect to find objects that emit no light or are otherwise undetectable. Next, we'll talk about missions that NASA as well as the ESA has launched to study planets and hopefully find Earth-like exoplanets. Launched in 2009, the Kepler mission searches for exoplanets using the transit method. It is currently monitoring some 100,000 stars, focusing lenses on one part of the sky. Kepler's goal is the creation of a statistical survey that predicts how many Earth-like planets likely exist in our galaxy. In 2003, the Spitzer Space Telescope was launched. Designed to observe objects in the infrared spectrum, Spitzer has proved to be a revolutionary tool in the characterization of exoplanets. The mission is the first instrument to directly detect light from an exoplanet, and its data has revealed the composition, temperature, and even likely wind patterns on faraway exoplanets. The Hubble Space Telescope's highly powered optics have produced some of the best images of exoplanets. The telescope caught an image of one in particular, and could have caught other exoplanets in its images before astronomers started particularly looking for them, leading to future research in the area.
The Earth Similarity Index is a way to rank astronomical bodies according to how close their physical parameters match those of the Earth. The ESI can be applied to planets in the solar system, their moons, and extrasolar planets. The ESI isn't actually a measure of habitability, but can serve as a guide for finding good candidates for future study. The ESI uses the formula seen here to determine similarity based on 4 attributes. Those attributes are radius, density, escape velocity, and surface temperature. This formula takes the measured value of an object and then compares it to a reference value for Earth for each attribute. The ESI values of all 4 attributes are then weighted and combined together to form a global ESI value for the object. An ESI of 1.0 is an exact copy of the Earth, while a value of 0 means the object is nothing like the Earth. An object with a global score above a 0.80 is considered to be Earth-like. Other than the Earth, the object in the solar system with the highest ESI value is Mars, with a rating of 0.66 to 0.70. As seen in the image, more and more exoplanets are now being discovered with ESI values above 0.70, with some higher than 0.90. This means that their size, composition, and temperature are nearly the same as the Earth's and may potentially be habitable.
The habitable zone is the area around a star in which an orbiting planet can sustain liquid water. Since liquid water is present, life as we know it can exist in this region. Water is a vital part of life. Any closer to the star, and the water will evaporate. Any farther, and it would freeze. Therefore, the habitable zone is the best known place to look for intelligent extraterrestrial life. When we look for Earth-like exoplanets, we search in the habitable zone. This region varies according to the size of the star. For example, a large star's habitable zone would be much farther out than a smaller star. For our own situation, we come just inside the sun's habitable zone, barely making the inside edge. Larger stars are generally ignored when searching for life-harboring planets, however, as they tend to have short lifespans. Most of the exoplanets we have found today come inside the habitable zone of red dwarf stars, the most populous star in our galaxy. These stars last much longer than our own sun, and life would have ample time to form and evolve on one of these planets. Scientists estimate that in our galaxy there are about 4.5 billion exoplanets orbiting red dwarf stars in their habitable zones, an almost overwhelming number. Scientists believe that we may be able to spot life on Earth-like exoplanets by looking at their outer edge. Infrared light, reflecting off chlorophyll in plants, gives the Earth a red edge when seen from space. If other planets have this red edge, they may also host vegetation. Scientists think algae and lichens may be one of the most likely life forms we find on an Earth-like planet, microbial life being the most likely. In order to check the atmospheres of these planets, they need to pass in front of their star. We have not yet found a planet that is the right orientation to Earth for this to work. Stephen Vogt, professor of astronomy and astrophysics at the University of California in Santa Cruz, told Discovery News that, personally, given the ubiquity and propensity of life to flourish wherever it can, I would say that the chances for life on this planet are 100%. I have almost no doubt about it. He was talking of Gliese 581g, an Earth-like exoplanet. Our group believes that this holds true for many of the Earth-like exoplanets around not only our galaxy, but also our universe.